This is Lesson 31 of our Calculus 3 series convergence tests. This lesson is about tests we can use to see if a series converges. Now in Lesson 30, we saw the geometric series, and we learned that for absolute r less than 1, the series converges, and it converges to a over 1 minus r. And for absolute r greater than or equal to 1, the series diverges. We also saw a test for divergence that says if the limit of the sequence terms is not equal to 0, the series diverges. In this lesson, we're going to cover several other tests for convergence. And they're all listed here in this first page, but we'll go through them individually. So let's start with what we saw in Lesson 30. We saw that 1/2 plus 1/4 plus 1/8 plus 1/16, etc. is equal to 1. And we found this by considering these numbers as distances on the real number line. Now I want you to consider these same numbers as areas. So for example, this box has height 1/2 and width 1, so its area is 1/2. This box has height 1/4 and width 1, so its area is 1/4. Here we have an area of 1/8, 1/16, etc. Now recall that these values are coming from the series 1 over 2 to the n. So on the same graph, let's plot f of x equals 1 over 2 to the x, or 2 to the negative x. We already know that these areas sum to a finite number. We already know that those areas sum to 1. So what does that say about the integral from 1 to infinity of 1 over 2 to the x? In other words, what does that say about the area under the curve here from 1 to infinity? Well, if we know the series converges, clearly the area under the curve is less than the series summation. So we know that this integral must also converge. Similarly, let's take a look at that summation as an area, except we're going to place the blocks 1 unit over to the left. So we're going to have our box of 1/2 area here, 1/4, 1/16, etc. And let's look at the same function, f of x equals 1 over 2 to the x. Here we can see that if the integral converges from 1 to infinity, then the series must also converge, because the series is less area than what's under the function curve. So recall from improper integrals, we can compute that integral, 1 to infinity, 1 over 2 to the x, by replacing our infinity with a b and taking the limit as b goes to infinity of this definite integral. So we integrate, plug in our bounds, take the limit as b goes to infinity, and we get that this limit is equal to 1 over 2 ln 2. That tells us this is the area under the curve of f of x equals 1 over 2 to the x from x equals 1 to infinity. Because this is a finite number, we could see by our graph here that this series must also converge. Now, of course, we already knew that the series converged, but I'm just trying to show here how the integral and the series are related. We have this integral test that says if we're looking at summation an and going from 1 to infinity, where an is equal to f of n, for f a continuous and decreasing function, and for f of x greater than or equal to 0, then the series and the integral either both converge or both diverge. So we can use graphs like these to compare the improper integral with the series. And we can see that if one diverges, the other must also diverge. If one converges, the other must also converge. So for example, let's take a look at the series e to the negative n and goes from 1 to infinity. Does this series converge or diverge? Well, let's consider the function f of x equals e to the negative x. We notice that this is a continuous decreasing function, and f of x is greater than or equal to 0. So let's take a look at the improper integral. Again, we replace the infinity with a b and take the limit as b goes to infinity, take the antiderivative, plug in our bounds, and take our limit. And here we can see that 1 over e to the b goes to 0, so we're left with 1 over e. So this is what the integral converges to. And so since the integral converges, we know that the series must also converge. I want to point out here, though, this is the area under the curve from 1 to infinity. This is different than the series summation. So the areas are not going to be the same. One might approximate the other, but the areas are not generally going to be the same. So we don't know what this series converges to, we just know that it converges. Now recall also from Calc 2 when we were studying improper integrals that the integral of 1 over x to the p going from 1 to infinity is convergent for p greater than 1 and divergent for p less or equal to 1. That gives us this information about series. We call these the p series. And the series 1 over n to the p, n going from 1 to infinity, converges for p greater than 1, diverges for p less or equal to 1. So for example, this is saying 1 over n to the 3 halves converges, 1 over radical n as a series diverges. Now let's consider the series 1 over n to the third plus n. Now it's not quite a p-series, but it's close to a p-series, and we want to see if we can use what we know about 1 over n to the third to help us get convergence or divergence information about this series. So we know that 1 over n to the third converges because this is a p-series with p equals 3. 3 is greater than 1. We also know that 1 over n to the third plus n is strictly less than 1 over n to the third for all n greater than or equal to 1. Remember, if we're adding something positive to the denominator, we're making a smaller fraction here. So that says for any partial sum, the partial sums here are going to be less than the partial sums here. So let's take a look at S sub n, the nth partial sum of the series we're interested in. We know this is going to be less than the nth partial sum of 1 over n to the third, which is less than the total sum. We'll call that S. So now, what do we know about this sequence of partial sums? We know that it's a sequence that's monotonically increasing because all of these terms are positive, and so we just keep adding them on, so we've got a monotonically increasing sequence. We know that it's bounded above by the sum of this series and below by the first partial sum, S sub 1. That means it converges. So that says our series converges. So what we did here was a comparison test. We compared our series to a series that we know converges. We said if the terms we have are less than the terms in a series that converges, well then this one must converge as well. So our comparison test here says if you have an less or equal to bn, both of those terms are greater than or equal to 0. If the series bn converges, then the series an must also converge. Similarly, if we have the series an diverges, and the bn terms are all bigger than those, then the series bn must also diverge. So let's take a look at this series here. We have 3 to the k plus 1 over 2 to the k. Now we know this is similar to 3 to the k over 2 to the k, which is 3 halves to the k, which is a geometric series. And we know that diverges because 3 halves is greater than 1. So let's see if we can make a comparison between this and this one. Well, we notice that if we're adding a 1 to the numerator, we're making this fraction bigger. So that says, in the notation of the comparison test, bn, the bigger one, is 3 to the k plus 1 over 2 to the k. An is 3 to the k over 2 to the k. What do we know? We know that series an diverges. That tells us that series bn must also diverge. But what happens if we have 3 to the k minus 1 over 2 to the k? We can't make this kind of comparison because the inequality goes the other way. But then what we have here is that we have a series whose terms are each less than a series that diverges. But that's not helpful. Just because it's less than something that's divergent doesn't tell us if this converges or diverges. It could be either. So we need a different test. The comparison test that we were just using isn't going to be helpful here. But when we look at the terms of this series, we're pretty sure that this should diverge because these terms are so close to 3 to the k over 2 to the k, especially as k goes towards infinity. So let's take a look at the limit comparison test. Instead of doing an inequality comparison between the two series, let's divide the terms of the series and take the limit and make a comparison there. So here we've got two series where the terms are all positive, and we want to take the limit as n goes to infinity of the ratio of those terms. So we'll take one term on top of the other, we'll simplify. Here we've got the limit as k goes to infinity of 3 to the k minus 1 over 3 to the k, which by L'Hopital's rule we can see for sure is equal to 1. So here we have a finite limit that's greater than 0. That's telling us that we have the same behavior between the two series. So just as we suspected, the series we're looking at also diverges. So this is another type of comparison test. It's not an inequality comparison test, but it's a comparison by dividing the terms of the series. Now keep in mind that this limit comparison test is also very useful when you have rational expressions in your series. Here we had exponentials in our series, but let's consider a case where we have a rational expression, like the series n going from 2 to infinity, 2n over n to the third minus 1. We look at this and we see that it's very similar to 2n over n to the third, which would simplify to 2 over n squared, and as a series that would converge. We know that by p series, right? This is p equals 2 here. But if we try to set up a direct comparison, the inequality would be going the wrong way. Because we have this minus 1 in the denominator, we know that our denominator here is smaller, which makes this entire fraction bigger than 2n over n to the third. And saying that we have terms that are bigger than the terms in a series that converges doesn't help us. This might also converge, but it might diverge as well. So a direct comparison is not helpful. Using the limit comparison, though, we recognize that both of these series terms are strictly positive, and so we take the ratio and the limit of that as n goes to infinity. So we're simplifying here, and we get limit as n goes to infinity of n to the third over n to the third minus 1. And we know that this limit is equal to 1, which is strictly greater than 0, and so the limit comparison test does apply. It says that these two series have the same behavior. And since we know that 2n over n to the third is 2 over n squared and that converges, so does the series we were given, 2n over n to the third minus 1. So when you see a series that looks like either a geometric series, if we could get rid of that term, or a p series, if we could get rid of the extra term here, think about making comparisons. And if the direct comparison doesn't work, think about the limit comparison test. Now let's take a look at the alternating harmonic series. We know that the harmonic series diverges, but what happens if we alternate signs with the harmonic series? Is that enough to give us convergence? What if we're looking at 1 minus a half plus a third minus a quarter, etc.? Is that enough to give us convergence? Well, let's take a look at the alternating series test. Alternating series test says if you have alternating sign, you have a negative 1 to the n plus 1 times a sub n, where a sub n is positive for all n. if the limit of those a sub n is equal to 0, and they're non-increasing, you have an plus 1 is less or equal to an for all n, then the alternating series does converge. And the proof here uses that the sequence of partial sums S2n, the even partial sums, is monotonic and bounded, and it uses that limit n goes to infinity an is equal to 0 to also show that the odd partial sums converge to the same limit. So we can use this alternating series test to examine convergence for the alternating harmonic series. Now notice the notation here. Usually we're calling whatever we have inside the series, whatever term that is, usually we call that a sub n. But now we're not calling that a sub n. We're separating the alternating sign from the rest of it. And we're calling the rest of it a sub n. So here in this notation, a sub n is equal to 1 over n. And that is positive for all n. Also notice that limit as n goes to infinity of a sub n is equal to 0. And that 1 over n plus 1 is less than 1 over n for all n. So all of these conditions hold for our alternating series, therefore the series converges. Now I want you to just keep in mind that even though this says negative 1 to the n plus 1, we know that negative 1 to the n can also give us an alternating sign. And it's okay to use the same test if you have negative 1 to the n in your series. Essentially, all that does is change the sign of all of the terms, but that doesn't change the convergence. So just keep that in mind, that that's also perfectly okay. Now, while we are talking about the alternating series test, I want to bring up the alternating series estimation theorem. If we have an alternating series that satisfies the conditions of the alternating series test, then the difference in absolute value between the total sum of the series and the nth partial sum is less or equal to the next term in the series, a sub n plus 1. And notice this is without the plus or minus sign here. So if we want to approximate the sum of an alternating series and have a specific bound on our error, we can use this theorem. So let's use it to approximate the sum of the alternating harmonic series that we were looking at with an error less than 0.0005. And so we're looking for, in this case, accuracy to 3 decimal places. So based on this inequality here, we want this difference to be less than 0.0005. And so what we're going to do is find an a sub n plus 1 that is less than 0.0005. So we set 1 over n plus 1 to be less than 0.0005, and we solve for n. This says n must be strictly bigger than 1,999. So using n equals 2,000 will give us a partial sum that approximates the entire sum with the accuracy we were looking for. So this is a nice little bonus that we get with alternating series that converge by using the alternating series test. Now let's take a look at the series negative 1 to the n plus 1 over n squared. If we got rid of this negative 1 to the n plus 1, in other words, if we took the absolute value of each term and looked at that series, we would have the series of 1 over n squared, which we know converges. And we know that limit as n goes to infinity of 1 over n squared is equal to 0. The n plus first term is less than the nth term for all n, and that all of these terms are positive. So by the alternating series test, we know that the original series with the alternating sign converges as well. Since we have this series with the summation of absolute value of an converges, we say that this series is absolutely convergent. And notice that this is a stronger condition than just saying convergent. Absolutely convergent is saying that even if you make all the terms positive, it still adds up to something finite. So we have this theorem that says if a series is absolutely convergent, then it's also convergent. And the proof looks like this. If we know that this series is absolutely convergent, let's take a look at this inequality. We have an plus absolute value of an greater than or equal to 0, less or equal to 2 absolute an. Notice here that absolute an is either an or it's negative an. If it's negative an, then this sum is equal to 0. If it's an, then this sum is equal to 2 an, or 2 absolute an. So we have this inequality. And we know that since it's absolutely convergent, the series 2 absolute an converges. Then by comparison, this series an plus absolute an must also converge, because those terms are less or equal to these. So if we look at the original series, we can write it as the difference of these two series, both which converge, therefore our series converges. So that's the proof of the theorem that says if a series is absolutely convergent, then it's also convergent. Now consider the alternating harmonic series that we were looking at. We know that that converges, but with absolute value signs, it does not, because the harmonic series does not converge. So we call a series like this conditionally convergent. Now let's take a look at the ratio test. Earlier we saw the limit comparison test, where we took the terms of two series that we were comparing and we looked at their ratio and the limit as n goes to infinity. Here we're taking a look at the ratio of two terms from the same series. We're taking a look at limit as n goes to infinity, absolute value of a sub n plus 1 over a sub n. And if this limit is less than 1, the series converges absolutely. If the limit is greater than 1 or is infinite, then the series diverges. If the limit is equal to 1, we don't get a conclusion from this test. Now this test is particularly nice for series whose terms have exponentials or factorials. And here we have both. We have an exponential with e, right? We have our index in the exponent, and we also have a factorial. So we're looking at summation e to the n over n plus 1 factorial. Now, just to get the notation clear, this is the nth term, so we're calling this an. And then an plus 1 is going to be e to the n plus 1. And then in the denominator, we have n plus 2 factorial, because this n is getting replaced by an n plus 1. So we have n plus 2 factorial. So now we want to take the quotient, a sub n plus 1 over a sub n, in absolute value. Notice here that we have n plus 1 factors of e in the numerator and n factors of e in the denominator, so we're left with just one factor in the numerator. And here we have n plus 1 factorial, so that's n plus 1 times n minus 1, all the way down to 1. And here we have n plus 2 factorial. So actually, this entire n plus 1 factorial cancels with this. And we're left with just the factor of n plus 2 in the denominator. So we're left with limit as n goes to infinity of e over n plus 2. So that limit is equal to 0, which is less than 1. So our series converges absolutely. Now, since all of these terms are positive to begin with, we don't really need to say absolutely, we can just say it converges. Let's take a look at one last test, the root test. This is particularly nice for any series with exponentials again, so we have something to the nth power, or if our index is k, something to the k power. Here we have series k is going from 4 to infinity, e to the k over k squared, all of that to the k power. And so we're going to look at the kth root of the absolute value of our term. So first of all, this is a positive term, so we don't really need to worry about the absolute value. So we're looking at the kth root here and taking the limit as k goes to infinity. The k and the 1 over k powers will cancel, and we're looking at the limit as k goes to infinity here, which is infinity. And you can get this by L'Hopital's rule. So that tells us that this series diverges. If our limit is infinite, the series diverges. Let's take a look at one more example. We have 3 to the n over n squared 2 to the n, taking the series as n goes from 1 to infinity. Now, even though it has a 3/2 to the n here, we might think of using the root test because of that. However, this n squared to the 1 over n is going to be difficult to deal with because taking this limit requires logarithmic limits. So instead, we should think about using the ratio test here. So we're looking at the n plus first term divided by the nth term in absolute value. So here's the n plus first term, dividing by a fraction and multiplying by its reciprocal here. Canceling, we're left with a 3 in the numerator, 2 in the denominator, and then we have n squared over n plus 1 squared. Remember, our limit as n goes to infinity when we have the same highest power is the ratio of the coefficients, which is just 3/2, which is bigger than 1. So what does that tell us in the ratio test? Let's go back up to the ratio test. If our limit is greater than 1, the series diverges. That tells us our series diverges. And with this, we'll end our lesson on series convergence tests.